All right, so we're going to start off looking at integration. We're going to solve a problem here. How to find the area under a curve. Fantastic. If it's a regular shape, not a problem. I mean, if it's a triangle, we've got a formula for that, a rectangle, formula for that. Other than that, we've got issues. So if it's this curve, y equals x cubed, how on earth are we going to do it? So we could estimate by drawing a rectangle, because we know the area of a rectangle. So I could estimate the area under this curve by saying, well, it's not a great estimate, but I know the area must be less than the area of those two rectangles, 1 times 1 cubed plus 1 plus 2 cubed. So what we call the outer rectangles, the one on the outside, going to give me an overestimate. But then I could also do an underestimate by drawing little ones. In fact, the first one's just a straight line, you'll notice. So those outer ones, 9. The inner ones, the ones that'll give us an underestimate, 1. Well, we know the area is somewhere between 1 and 9. Not a great estimate. I suppose the logical thing to do would be to average that out. Okay, we're going to estimate it out at 5. Actually turns out to be 4, by the way. So, well, how do we get a better estimate? Draw more rectangles, so we'll make them smaller. So that way the overestimate's not as big as it was. So now I can say the area of all those, so I know it's going to be smaller than 5.76. And the inner ones, and it must be bigger than 2.56. So we've trapped it a smaller amount. Average of that's 4.16. We're getting closer. So what the heck? Let's make 10 rectangles. Lots of little, here we go. So we know it's less than all of that, which is 4.84. Now the inner rectangles, and that's 3.24 average, 4.04. So now we're really getting close. And I could do it again. I mean, ideally, I'd like the width of those rectangles to be what? 0, yeah. Because obviously the smallest I can get it, the best the estimate's going to be. Well, we can't make it 0, but that's where our idea of limits comes from, that we were talking about previously with calculus. So let's see what happens. So I've now got just a random curve. So let's have a look at one of these rectangles. So there's one of the rectangles that, well, you know, we'd like that width to be 0. I'm going to define some function, a function that will give me the answer of the area. And area C will be the function that gives me the area from 0 to C. Area X will give me the area from 0 to X, and then the difference between the two will give me the area of that rectangle. So that particular rectangle, now I know it was curvy on top, but if we're trying to make the width 0, then the difference between those heights is going to be nothing, isn't it? So let's pretend it's nice and straight. But it'll be whatever the difference is, the x value minus c value by function x. I mean, it could have been function c as well, because we're saying they're going to end up being the same thing. So area x minus area c approximately equal to x minus c times that function value. Rearranging that, function x, because we know the equation of the curve, function x will approximately be that this area function that I want to find minus area c over x minus c. Of course, I could rewrite x, instead of calling it x, I could call it c plus whatever the width of the rectangle is. So I could call it c plus h, which means on the bottom I'd have c plus h minus c, which just leaves us with h, whatever the width of the rectangle is. And ideally, remember we said we want that to be as close to 0. So let's find the limit, and that's starting to look familiar. The limit as h approaches 0 of ac plus h minus ac over h. Okay, I've got a c there instead of an x, but remember we're assuming h is approaching 0, and so x and c would be the same thing, because as h approaches 0, c will approach x. And now it's looking real familiar. It's just that I've got a capital A there. Well, it's our first principles formula, basically. Well, so that's the derivative. It's the derivative of that area function that I'm trying to find. So what we're saying is the function of the curve, and we know that equation, that is the derivative of this function we're trying to find. Well, so then all I've got to do is find the primitive function. Let's go back and see what that is. So what ends up happening, if I want to find the area between 2 points, A and B, there's the notation we use, the integral symbol, which is the long S. So it's actually an S. I don't know whether you realise that or not, but it's an S. It means sum. We're summing up all these rectangles. So, and we're going from A to B, and it's of this equation, function x. And the answer will be whatever the primitive function of function x is. We'd sub the b value in, and we'd sub the a value in, and we'd come up with an answer. So it's lovely, and then all we've got to do is, use integration, find that primitive function. Find the area, so let's now find that exact value. Integral of x cubed dx, add 1 to the power over the power, sub in, yes indeed, we got 4 units squared. 4 units squared. So we could do that to any curve, of course. X squared plus 1, add 1 to the power over the power. Notice in my answer for this one, 22 and 3, I didn't put units squared down. Because in this case, it's not actually an area. I'm just saying, find this integral. So it's just a number. If it's an area, all right, I'll put units squared on it. You could have negative indices. Add 1 to the power over the power. Be careful with your negatives. Sub in. There you go. 9 over 800. Here, this one's interesting. d dx of function t to t. Integration and differentiation are opposites or inverses, so they cancel each other out. So what you're really doing is saying, hey, I want to differentiate the primitive function. Well, if you differentiate the primitive function, you're back to where you started from. So you actually end up with the derivative of function x minus function c, function x minus 0, and so it always just turns out to be function x. Doesn't matter what c is. Doesn't matter what c is. Okay.